In this video, we're going to talk about and probability. And what we're moving into is probability that we have formulas for and kind of understanding the formulas and understanding the examples and why they fall under those certain formulas. Okay, so this one's really clear cut, this example, and then we're going to get to less clear cut examples and explain why it's the same. What is the probability when you flip a coin, you get heads, and when you roll a die, you get a four? So what's happening is two things. You're flipping a coin and you're checking to see if you get heads, and then you roll a die and you're checking to see if you get a four. Okay, so there's two events going on here. The first event is that we get the coin shows heads. The second event is that the die rolls a four. And we want both of those events to happen. Okay, so the first thing we do is we flip our coin. So the probability we're going to get heads is 1/2. So that's the probability of E. And then the probability that we will roll a 4 on a die is 1 out of 6. Since we're talking about six-sided die, that's the assumption. They'll usually say if it's not six-sided, okay? And what we'll do is, because it's an and probability that one has to happen and then the other, we are going to multiply these two. Sorry, this is the probability of F. Okay, so that ends up being 1/12. That's the probability. We flip a coin, we get heads, and then we roll the die and we get a 4. Okay, so what I'm kind of highlighting here below is the formula for this scenario. So what we have is the probability of E and F equals the probability of E times the probability of F. And it's that basic formula we'll use when we're talking about and probabilities. Okay, now let's kind of change the wording a bit, but we're still really looking at the same thing. So let's say this time I say, what is the probability you flip a coin twice and get 2 tails? It's actually the same type of question, because what's happening is we flip a coin once, but in order to complete the question, we have to flip the coin a second time. So there's two events, the first coin toss and the second coin toss. So in the first coin toss, we'll call that E. Gets tails. And then the second coin toss gets tails again. Sorry, that's a sad looking version of the word second. Okay, so in this case, probability that we get tails is 1/2 both times. So that's 1/4. So we consider this an and probability because both things have to happen. Wow, that's not how you spell happening. There's two N's. Two things are happening. Okay. Let's look at another example. Kind of changing it a little bit again. If 9%, actually here, before I do that example, let me explain one concept really quick. So what we've been doing is looking at what are called independent events. And independent events mean that the events don't affect the probability of each other. So the events don't affect the probability. I should say, actually, here, let me say that a little cleaner. Wow, that was very poorly worded. One event doesn't affect the probability of another event. There we go. So in the case where you flip the coin, when you flip the coin the first time, that doesn't affect what happens the second time you flip the coin. Like the coin doesn't care what happened the first time you flipped it, right? Like you flip that coin, it's completely independent of the second flip when you flip the coin again. Same with the first example, rolling the die and flipping the coin. Flipping the coin doesn't affect what happens when you roll the die. It doesn't. They don't affect each other, okay? So let's look at another example. Let's say I tell you that if 9% of the US population has green eyes, then what is the probability to randomly selected OCCC students have green eyes? All right. So in this scenario, first of all, we're kind of looking at probabilities being given to us in this case. So we're talking that when you say that 9% of the population has green eyes, you can interpret that to mean that there's a 9% chance somebody has green eyes or somebody's born with green eyes in the US. Okay. That's how we could kind of interpret that. Now, the question asks, what's the probability that we randomly select two OCC students and have green eyes? So in this case, we still have two events. The first event is the first student has green eyes. And the second event is the second student has green eyes. Wow, there's supposed to be an E in the word student. There we go. So there we go. There's our two events. And they are independent. And the reason is they use this phrase right here, randomly selected. Whenever you say randomly selected, that means that they're using one of the sampling processes we've talked about. So they're not allowing these two students to just be like pulled out of a crowd. If two students are walking together and we just grab them both as our two randomly selected students, that's not random because they were together. Could they be siblings and therefore the chance of them having green eyes is higher? Yes. So we're assuming when they say randomly selected, they have nothing to do with each other and therefore are independent. Okay. So in this case, the probability that the first student has green eyes is 9%, which I'll write as 0.09. So I'm writing it in its decimal form. And that the second student has green eyes is also 9%, which I'm writing as 0.09. And I'm going to multiply those together. Now, I put it in parentheses just because of the decimal place. It's easier to see the multiplication this way. All right. And if you multiply 0.09 by 0.09, you will end up with a very small probability of 0.0081. So a less than 1% chance that this would happen. Why? Well, because the odds that somebody has green eyes are already low to begin with. To randomly select two people with green eyes, it's just not a very high probability that that's going to happen. Okay, now, if the two events are not independent, they are therefore dependent. And if they are not independent, that means that they do affect the probability. So one event affects the probability of the second event. Or other event. Okay, so what's kind of fun about this one is to refer to a deck of cards. Okay, so I did actually try to just look at a deck of cards online, like just to give you guys a picture. So in case you don't know what a deck of cards looks like, I'm going to let you stare at it really quick. Here, let's see if it works. Woohoo, there it is. Okay, I'm gonna make it a little bit bigger, but that is a standard deck of cards. Okay, so in a standard deck of cards, we have 4 suits. The first one is, in this particular little picture I have here, is called spades. Second one is hearts. Third is diamonds. And fourth is clubs. Oops, clubs. There we go. In each of these categories, there are 13 cards. And if you add that together, that's a total of 52 cards. And each of them have the same cards. The first card being an ace, the second card being a 2, which are called the number cards, all the way down to these last 3 cards. This card right here is called the jack, the queen, and the king. And like I said, I just don't want to assume that everybody knows what the standard deck of cards is and what they're all called, okay? This is in your notes for the class and in the textbook. So for if any reason you need to relook this up, you can, okay? But you are expected to know the deck of cards for the exam. It's kind of a standard probability idea. So we are going to work with them pretty extensively. And I do want you to memorize these basic facts, okay? Okay, so we're going to use the standard deck of cards to ask a couple probability questions. Let's look. First question. So let's say, find the probability of, okay. And then here we'll kind of create some scenarios. So the first scenario is you draw 2 queens from the deck with replacement. Just write that down and then I'll explain. Okay, the word draw. Draw means you're pulling a card from the deck. Common language with that is the word draw. You draw a card from the deck, okay, of cards. So we're drawing 2 cards from the deck and we're wanting to know the probability they're both going to be queens. And then they also use this little thing called with replacement, meaning we draw a card from the deck, we look at it, we put it back into the deck, shuffle it again, and then draw another queen, okay? That's the idea. So probability that we'll draw a queen. So first of all, how many queens are in the deck of cards? Well, there would be 4, 1 for each suit. So we have 4 queens total. Out of 52. Then we put the card back in and we still have 4 queens to draw from out of 52. All right, now I'm going to multiply this on my calculator. Actually, I'm really just going to multiply 52 on my calculator. So that gives me 16 out of 2704, which I'm just going to go ahead and write as a decimal. I'm going to switch to decimal format. So that comes out to 0.0059, and then there's more decimals after that. But I think 0.0059 is a perfectly acceptable number. I would also be okay with you rounding to 0.006. That's okay as well. Okay, so this happens to be an independent event. Because, or independent events, because we put the card back into the deck. But what if we don't? What if we just draw 2 queens? What if that's what we're asked, that you draw 2 queens? Now, in this case, we're no longer working with the same deck. The first queen we draw out still has a 4 out of 52 chance of being pulled, but the second queen is now only 3 out of 51 because we only have 3 queens left and we are 1 card short because we already have 1 card in our hand, okay? So in this case, we have now changed to dependent events. And the reason is the first card pulled out of the deck affected the probability of the second event happening. So drawing a queen the first time changed the chance that what the probability was for drawing a queen again. Okay, so here, let me get my calculator and calculate this. So this time I get 12 over 2,652, which I'm just, like I said, going to go ahead and divide into a decimal. And this time I get 0.0045. So the probability went down. By the way, both of these events have a less than 1% chance of happening. The chance that you grab a queen out of the deck and then grab another queen is actually very low. Okay. But now it's even lower when we don't replace the first card. Okay. So that is an example of a dependent event. Okay. So let's try this one. Let's say this time I draw a queen. Oops. Draw a queen and a 3. Okay, so just like the queen, there are 3s in all 4 of the suits. So therefore, the probability that we draw a queen is 4 out of 52, but we're not assuming replacement because they didn't say that. Okay, so we're holding on to the queen in our hand. So how many 3s are left in the deck? Well, there's still 4 3s in the deck. However, there is only 51 cards because I'm holding one of the cards in my hand. So this gives me 16 out of 2,652, which I will then divide and get 0.006. Technically 0060, kind of writing it like that so I could see this actually has a higher chance of occurring than the very, sorry. This has a high chance of occurring, a more higher chance of occurring than the last one. Okay. All right. Actually, it has a really good chance of occurring. It's a better chance of occurring than even the first scenario. And the reason is the chance of getting a 3 actually went up a little bit because I have one less card in the deck. So it improved the odds that I would pull a 3 as the second card. Okay. So it does have a little bit better odds. So this is still an example of a dependent event because the probability of getting a 3 did change simply because the number of cards in the deck aren't 52 anymore. So it's still dependent events here, simply because the second probability did change based on what happened with the first card. And there you go. That is and probabilities.